Lecture. I am Dr. A.VELMURUGAN, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Chettikare, Dharmaburi. In this video lecture from upcoming semester, Thermal Engineering 2, Unit 1 Steam Nozzle, Unit 2 Steam Boiler, Unit 3 Steam Turbines, Unit 4 Cogeneration and Waste Heat Recovery System, Unit 5 Refrigeration and Air Conditioning System. From this Unit 1 Steam Nozzle, different types of nozzles, condition for maximum discharge flow, types of nozzle, effect of friction in the nozzle, the maximum discharge through nozzle, condition for maximum discharge through nozzle, define critical pressure ratio and critical pressure. Finally, we have discussed about the metastable flow. From the syllabus point of view, from Unit 1, you can study about the types and shape of the nozzle, maximum flow discharge through nozzle, critical pressure ratio, and we can study about the problem point of view. From Unit 2, steam boilers, water tube boiler, fire tube boiler, and comparisons, mountings and accessories are used for the boilers, various types of fuels used for the thermal power plant, solid, liquid and gas, and finally we should find out the performance calculations. From Unit 3 you can study about the steam turbines, impulse turbine and reaction turbines, velocity compounding, pressure and velocity compoundings and governing of the turbine. From Unit 4 you can study about the cogeneration waste heat recovery system. From that cogeneration system, from that thermal power plant, we have to used for the flue gases for useful application, and also from the gas power plant we have to using the flue gases for the useful application from the based upon the cycle, bottoming cycle or topping cycles, and waste heat recovery system from the recuperator and different types of heat exchangers are used for that from that application point of view. And finally we can study about the economic aspects from the waste heat recovery system. Fifth unit you can study about the refrigeration and air conditioning system. From that vapor compression refrigeration cycle, vapor absorption cycle, refrigeration cycle, cooling load calculations, cooling towers. From that, from this slide we can discuss about the steam nozzle. From the photographic view of the steam nozzle will be show. From that, from this slide we can, from this figure we can discuss about the, from the steam nozzle is to impinges to rotate the turbine blade from that 40,000 rpm. From the, for example, from the simple impulse turbine we have to rotate from the 40,000 rpm. From that, velocity of the nozzle is around 1100 meter per seconds. We have to rotate the turbine blade, it is coupled with the generator to produce the electricity. From that introduction point of view, what is the steam nozzle? The steam nozzle is a passage of varying cross section area which converts heat energy of the steam into kinetic energy. The main use of the steam nozzle in a turbine which produce the jet of steam with high velocity. From that, steam is generally from entered from that steam nozzle. The high pressure steam is entered to the nozzle. From that, pressure energy or potential energy is converted into kinetic energy from the nozzle. From that, exit condition of the nozzle is the high velocity around 1100 meter per second. The smallest section of the nozzle is called as throat. From the nozzle there is a convergent throat and a divergent section is called. From the smallest section is a throat. It may be noted that the steam is entered the nozzle with high pressure and negligible velocity, but leaves the nozzle is high velocity and small pressure. The pressure at which steam leaves the nozzle is known as a back pressure. So from the year of 1978, the Swedish engineer G.P. level to construct the simple impulse turbine to rotate the turbine with the help of the maximum speed of 40,000 to 1 lakh rpm, and the high velocity is around 1100 meter per second. After we have to reduce the speed to get the useful energy and also to improve the efficiency of the turbine to construct the velocity compound turbine and pressure compounded turbine and pressure and velocity compound turbine. So we have to utilize that, we have to reduce the losses from that nozzle from the steam velocity. So we have to using from that velocity compound turbine. That steam turbine is generally used for the thermal power plant, nuclear power plant to produce the electricity, and also it is used for the mainly from that marine applications, from the large ships and ocean liners and submarines to drive power absorbing machines like large compressors, blowers, fans and pumps. From this slide we have discussed about the flow discharge through the nozzle. Generally the nozzle is a duct that increase the velocity of the flowing fluid to expand the pressure drop. A duct which decreases the velocity of the fluid and causes a corresponding increase in pressure is known as a diffuser. The same duct may be either nozzle or a diffuser depending upon the end condition across it. If the cross section area is duct is decreases gradually from inlet to exit condition, this duct is known as a convergent section, convergent nozzle. From that, conversely, if the cross section is increases gradually from inlet to exit, this duct is known as a divergent section. If the cross section is initially decreases and also it is increases, this duct is known as a convergent and divergent section nozzle. The minimum cross section such duct known as a throat. From this figure we have discussed about the types of nozzle. From here the convergent nozzle and divergent nozzle. From the convergent nozzle the Mach number is less than 1. From the divergent nozzle is the Mach number is greater than 1. Mach number is nothing but a velocity of the fluid divided by velocity of the sound. From the high pressure steam is entered to the convergent nozzle. From that inlet condition and exit condition, from the inlet condition the pressure P1 is high pressure, the velocity is very small from that inlet conditions. From here the high pressure steam is the potential energy is converted into kinetic energy from the exit condition. From that divergent nozzle, that is the pressure P1 and V1, from here the velocity will be highly increased from the divergent section. From the convergent section, that is a critical pressure is equal to back pressure or critical pressure is greater than to the back pressure. From the divergent section the back pressure is less than to the critical pressure. From the subsonic speed the Mach number is less than 1. A decrease in the area increase the speed of flow. From second point, the increase the supersonic flow, the Mach number is greater than 1. The effect of the area changes are different. So from this slide, as I told about you, from that there is a three section. One is a convergent section, throat section and a divergent section. From the convergent section the Mach number is less than 1. From the throat section Mach number is equal to 1. From the divergent section is Mach number is less than 1. From this figure, from the convergent nozzle section is very small compared to divergent section. Nozzle is the section is very long. From the divergent section only the friction will be happen. From the friction is that is the high pressure steam is touched the metal surface, there will the friction will be happen. And also if the friction is that automatically the heat will be transferred from the nozzle section, the drainage fraction is it will be reduced. Again the heat is goes to the same steam, means the drainage fraction will be improved. From that first section is a convergent section, second section is a throat section, third section is a divergent section. From that from this topic, flow of steam discharge through nozzle based upon the steady flow energy equations. From the steady flow energy equation from the nozzle, the work done equal to 0 and the heat transfer equal to 0, the potential energy equal to 0. We got assumed from the first point is to steady flow, there is no heat transfer, that is isentropic flow, Q equal to 0. From that the change in potential energy are negligible, equal to 0, work done equal to 0. Based upon the steady flow energy equation, law of conservation of masses, that is a Q plus M into H1 plus H suffix 1 plus 1 by 2 V1 square plus G Z1 equal to W plus M H2 plus 1 by 2 V2 square plus G Z. From here the potential energy is so negligible, work done also negligible, heat transfer also negligible. Finally we get the enthalpy H1 is equal to H2 plus 1 by 2 V2 square. Finally we should find out the exit velocity of the nozzle is V2, V suffix 2 is equal to square root of H1 minus H2 into 1000. From the steam table we have to convert to kilojoules. From the enthalpy kilojoules per kilogram we convert to meter per second, we add 1000. Finally we get to find out the final velocity, means 44.72 square root of H1 minus H2. From the steady flow process, that is the A1 V1 by specific volume is equal to A2 V2 by specific volume of the outlet condition. Here the A is a cross sectional area, here the V is a velocity in meter per second. Based upon this figure, from y-axis is the enthalpy, from x-axis is the entropy. From here the P1 is the initial pressure, from P2 is a condenser pressure or back pressure. From the theoretically process 1 and 2 is a theoretically isentropic expansion process. From process 1 and 2 dash is a actual process. From the theoretically, that is Theoretically, that from the isentropic expansions happen from the pressure P1 and P2. From here there is a saturation line. From the below saturation line is a wet steam. From above saturation line is a superheated steam. From that, based upon the del Hs is equal to H1 minus H2. Del H is equal to actual condition H1 H suffix 1 minus H2 dash. Finally, we find out the nozzle efficiency is equal to del Hs by del H actual. We get the theoretically from the exit theoretical velocity from that exit condition of the nozzle is square root of 2 into H1 minus H2. From actual conditions, the square root of 2 H1 minus H2 H2 dash. Finally, we get the square root of 2 del H actual. We should find out the coefficient of the velocity or nozzle efficiency. We have to get the coefficient of velocity is equal to V2 theoretical by V2 actual. From here, finally, we find out the nozzle efficiency, same as the nozzle efficiency. We should consider from the problem point of view. If you are asking from the most of the problem is asking from the from the theoretical isentropic expansion process. If the actual expansion, actual condition will be asking from the, we should find out the nozzle efficiency from the final exit velocity. From this slide, from this figure, we have discussed about the from that process is happening on from the nozzle to generator. From that the high pressure steam is entered to the nozzle section. From here the initial velocity is 0, that pressure is high. From the exit condition, that the pressure will be reduced, the velocity will be increasing, that is a kinetic energy. And from this dotted line is shown from the friction will be happen from the nozzle section. From the kinetic energy from process 1 and 2, we get the exit condition is a kinetic energy, that the energies goes to the turbine, that the kinetic energy is converted into mechanical energy. We get the efficiency of the turbine. From here, half into mv square 2 into efficiency of the turbine, we that from it is that the energy goes to the generator, that the mechanical energy is converted into electrical energy and also generator efficiency. Finally, from the output is 1 by 2 v2 square efficiency of the turbine and efficiency of the generator. So as I told about you earlier, from that figure, that is a there is a from the types of nozzle is a convergent nozzle, divergent nozzle. Convergent nozzle is used for the generally used for the hydroelectric power plants, but in the thermal power plant, most of the power plant we have to using for gas power plant or thermal power plant, we have to using for convergent or divergent nozzle. Generally, we have tell about the nozzle name as a CD nozzle. From this, there is a three section. One is a convergent section, another one is a throat section, another one is a divergent section. Based upon this section, from the convergent section is very small compared to divergent section. From here the convergent section is a Mach number is less than 1. From the throat section is Mach number is equal to 1. From the divergent section is a Mach number is greater than 1. From here the high pressure steam is that high pressure steam or potential energies enter to the nozzle section from the inlet condition. From here the pressure is high, velocity is low. If the high pressure steam is entered to the convergent section from the throat, there is a critical pressure will be happen from the throat section. From the m is equal to 1. From the throat section is a very small section compared to other section. The high velocity steam is delivered from that from the divergent section. The high velocity stream is around that high velocity is 2 impinges to rotate the turbine blade from that high velocity around 1100 meter per second. So from that if you impinges to rotate the turbine, then only the shaft will be rotating and to produce the electricity. So to impinge the bucket wheel from that from the impinges to rotate the impulse turbine from the high rpm. So generally from the impulse turbine, that is a D level turbine, is rotating for 40,000 rpm to 1 lakh rpm. Maximum condition is 1 lakh rpm. That high velocity is around 1100 meter per second to rotate the turbine. So finally, from the convergent and divergent nozzle and the shapes of the nozzle and maximum discharge flow through the nozzle, everything from the design aspect, we should find out the critical pressure is equal to critical pressure. And also from the problem point also, we should find out the critical pressure, maximum discharge and theoretical velocity and actual velocity. And also we should find out all the parameters with the help of that convergent and divergent nozzle. Thank you.